speaker of the Protect Academy that we've been holding for the last couple of weeks. And I'm very pleased to introduce my colleague and good friend, Akram Al-Shawabke. He is the George Snell Professor of Engineering here at Northeastern University. He is also the PI and the director of the Protect Superfund Research Center. His expertise is in soil and groundwater remediation, electrokinetic and electrochemical processes, contaminant fate and transport, and environmental restoration. He received his PhD from Louisiana State University, and he has been here at Northeastern since 1997. In addition to the Snell Professorship, he has many other distinctions, including he's a Fulbright Scholar, he is a National Science Foundation Career Awardee, and he is a Fellow of the American Society of Civil Engineers. With that, I'm going to turn it over to Akram, who's going to give us the final installment of the Protect Academy on soil and groundwater remediation.
Thank you, Tom. And before I start, I would like to also thank our training corps team for organizing this academy. I think it was a great opportunity for us to provide some introductions on the topics we talk about. Tom, Kristen, Melanie, and Terry have been great coordinating this academy. And I also want to thank our speakers, John Meeker, Rita Lacaruso, and Ingrid Badia on the topics they've covered up to date. So what I'll talk about is give just an overview of on soil and groundwater remediation, non-expert kind of an overview. And before I start that, I want also to acknowledge the NIEHS, the Superfund Research Program, who are supporting our training corps and our research activities in Protect. And as mentioned before, our Protect Center looks into contamination in Puerto Rico. This is just a general overview of what we do within the Protect Center, looking at contamination from source to outcome, with a focus on preterm birth as the major health issue. And we're looking at Puerto Rico because of a high level of contamination and high rate of preterm birth in Puerto Rico. We have 5 projects that describe and evaluate the problem from source to contamination, and the projects are supported by cores to enhance integration and increase impact from the products of our center. So now moving forward, what I'd like to talk about today is an overview. So we talked about contaminant fate and transport in the first session, and that will give some background on the things that I'll talk about. But what I'll do is also talk about contamination, extent of soil and groundwater contamination, why is remediation is critical and needed, and we'll talk briefly about soil and contaminant properties that would affect how contaminants move and also how we would approach remediation. I'll give an overview of remediation technologies, and then give just quick examples of soil vapor extraction, bioremediation, solar power remediation, the process we're working on. And I have one more item that's not listed here, just talking about other relevant issues to remediation. So we'll start with an overview of contamination, talk about the extent of soil and groundwater contamination, specifically in the U.S., and the factors that the soil and contaminant properties that affect that. So over the past 3 decades or so, there's been a lot of work on remediation, cleanup of contaminated sites. But with all the success that is there is still significant contamination in the U.S., and many sites are listed or removed over time, and many contaminants are added to the list of contaminants of concern. Some sites are really difficult to deal with and most problematic, and those are the ones that tend to have some persistent contaminants, some source zone where things are sticking or staying. It's difficult to break down, and those sites that have some heterogeneity of contaminants as well as site heterogeneity, those affect the ability to extract the contaminants and kind of make them in a way that we can remove them or treat them. Cost is significant because we deal with, again, a heterogeneous media and very complex chemistry and geochemistry that affects how contaminants stay and move in the soil. Contamination is significant. This is a recent report by the NRC about contamination in the U.S., including, of course, the Superfund and other federal agencies, underground storage tanks. And you can see there are many sites that are still contaminated in the U.S., and the estimated costs are in the billions of dollars. According to the report, these are estimates. There are conservative estimates, so it's expected to be more. And the EPA, there are other estimates I've seen in the past. One of them, EPA 2004, was looking on more than $200 billion for remediation over the next 30 years. So it's a big problem, and it's a costly problem, and it has impacts on water resources and human health. Sources of contamination, many of us deal with the Superfund research program, and we've exposed to many types of contaminants or sources of contaminants that affect soil and groundwater. And this is just a quick overview. These contaminants come from agriculture, come from industry, come from all kinds of sources, municipal landfills or landfills that are leaking, or improperly engineered landfills, improper dumping of waste. And that tends to contaminate soil and groundwater in different ways, because we have different chemicals and we have different soil characteristics that tend to hold these contaminants. To be able to understand again how contaminants move and be able to remediate and clean up contaminants from soil, we need to look into the site characteristics, the physical soil and groundwater properties, and then we need to look at the contaminants properties and how these interact with the soil and groundwater. For site, we talk about site characterization. Hydraulic conductivity or permeability, this is how contaminants move in the ground, how water moves in the ground, and controls how contaminants move accordingly. Soil texture and type, if we have a certain gradation, affects permeability. It affects also the soil contaminant interactions. Organic matter, if there's presence of organic matter in the soil, it will affect the ability to hold contaminants, especially organic contaminants. Cation exchange capacity, this is a property of soils. When we have clay-like soils, they are typically negatively charged, and they have a capacity to hold cations, and these cations sometimes can be contaminants that tend to stick, and then it's hard to remove them once they're stuck on the soil particles. Contaminant properties, another variable, other important factors that we need to keep in mind. Solubility of the contaminants. Geochemistry, how do they interact, again, with soils. Biodegradability, they degrade or not. And volatility, if we're talking about contaminants above the groundwater table. So what I'll do is go over these factors in general, and that will lead us to, again, remediation. The groundwater hydraulics are very important. When you talk about contamination, things go into the ground, soil are heterogeneous. You have aquifers, you have these layers that are very porous, where water moves easily, and Ingrid talked about groundwater flow contaminant transport in the first lecture, and give you an overview of these systems. However, over here, we need to be careful also with the different components that we are looking at. If we have an unconfined aquifer versus a confined aquifer, that is going to affect how we do things. If we are in the VADO zone, which is the partially saturated zone above water table, that will affect how we approach things. If we have an aquitard that separates our and that aquifer, is there potential for leaking from one aquifer to another? Could be an upward or a downward, depending on the pressure situation that these aquifers are in. And the piezometric surface or the groundwater level, that affects the direction of the flow, and where the source is, it affects where the contaminants are moving. Is my source over here in this zone, then it will tend to contaminate the soil down gradient, and that also will affect how we approach remediation, talk about containment or active or source zone, things like that. So these are just an overview of the soil parameters that are relevant. Soil type and gradation, it really defines contaminant transport and also the interaction of contaminants with the soil solids. We typically think of sand as a relatively an inert particle where there isn't much sorption or interaction between the contaminants and the sand particle. But if we have a fine-grained particle like a clay particle, there is a surface charge on the clay particle, and there is significant physicochemical interactions between the clay particle and the contaminants that are in the solution. And those can complicate how we approach the remediation. Soil water saturation, are we talking about contaminants above the free water surface in the partially saturated zone, or are we talking about the fully saturated zone below the groundwater table? That if you have contaminants that's volatile and sit above the groundwater, then they will contaminate and generate some vapor contamination. I mentioned hydraulic conductivity and permeability affects, again, the flow of contamination and direction. Soil organic matter and cation exchange capacity, those affect how contaminants tend to stick or move within the soil. So they tend to retard the transport of contaminants when they're present. Now, contaminant type, unfortunately, we're dealing with all kind of contaminants, inorganics or organics, some less. We're talking about heavy metals, petroleum compounds. These are the organics and chlorated compounds. Their chemistry is different. Their chemistry is complex, or biochemistry too, when we talk about bioremediation. In geochemistry, their interaction within the pore fluid and the soil particles. Two major mechanisms mentioning over here. One of them is the adsorption or the sorption process, where contaminants tend to stick on certain soil particles depending on the soil particles and the organic content. And the redox reactions, where contaminants change form from one redox condition to another, and then they could change the toxicity level and their interaction with the soil based on these redox conditions. Solubility is a factor, especially when we're looking at organics that are dissolved within the source zone and the groundwater. Volatility is important when we talk about above groundwater table. And biodegradability is the ability to break down the contaminants by bacteria that's present in the soil, and what conditions and what rates would these happen. That also can be a tool and is a tool used for remediation. Briefly, sorption. I'll just go over some of these mechanisms since they are relevant, and I think Ingrid again talked about them at the beginning, but I wanted to go over them quickly. Adsorption, again, chemicals stick at the interface between the soil solids and the water, and the affinity of sorption depends on the soils, depend on the organic contents, depend on the cation exchange capacity, which is a soil type of thing, and it depends on the chemical type that we're looking for. For metals, usually electrostatic. Clay particles are negatively charged, so you have cations come in and sit and stick on the clay particle surface. For organics, it tends to depend on the soil organic matter. And this chart shows on the y-axis the sorbed concentration versus the concentration in the poor water kind of a thing. So it shows that we can have different kind of relationship between the amount of contaminants that are stuck on the soil particle versus the amount that's in the water that is mobile. And that is critical for remediation, because you can do pump and treat, where you can take all the poor water that's contaminated out of the soil and clean it up, to go and find out that now you have release of the contaminants that are stuck on the soil particles. And that makes pump and treat a process that takes so long to clean up, to be able to clean up a contaminated site. Sorption depends on again, the contaminant and the geochemistry. So the pH is a factor. If you look in this chart, depending on the different cations that we have, and this is with the electrostatic sorption, on the y-axis, the percentage of the contaminant that is bound to the soil particle and become immobile. And it shows that it changes as a function of pH, and the reason is that these contaminants change chemistry as pH, but most importantly, the pH changes the properties of the soil particle surface, and that changes their ability to adsorb or desorb these cations. So pH becomes a factor. That's why when we go and wanted to do some metal measure metal concentration in soil particles, we flush them with acid so that we completely take the chemicals out of the soil particles and put them into solution, and that will tell us what is the total in the soil. I mentioned about redox chemistry. This is an example of chromium where its redox will change, its form will change in whether it's chromium-3 or chromium-6. That's a function of the redox potential on the y-axis, which is a measure of the electron activity within the pore fluid in groundwater. And on the x-axis is the pH of the system. So depending on the pH and the redox potential and what's present there, what type of minerals we have, chromium will change its form from a chromium-3 to a chromium-6. And why is this important? Chromium-6 is toxic, chromium-3 is not considered toxic. And then the other thing is that chromium-3, if we have clay type of media, chromium-3 will stick on the soil particles, while chromium-6 will go into the solution and becomes mobile. So the pH and redox conditions are very important when we talk about contamination. And we can go on and on the geochemistry and the factors that affect contamination distribution and patent transfer remediation, because we have, as I mentioned, many types of contaminants and many types of soil media and interactions. Let me go back to the other factors, solubility, volatility, and biodegradability of the contaminants, and I'm giving an example when we talk about these with the NAPLS. NAPLS are the non-aqueous phase liquids. These are separate phase hydrocarbons classified by specific gravity. L-NAPLS, they're lighter. These are the hydrocarbons that are lighter than water, and D-NAPLS are the ones that are denser than water. The lighter than water tends to float on top of the water table, those like the gasoline, diesel, jet fuel, while the D-NAPLS tends to sink below the water table and result in more contamination. Examples of D-NAPLS, chlorinated solvents, PC and TCE, some of the contaminants we work on in Puerto Rico, wood preservatives, PAHs, which is the polyaromatic hydrocarbons, and they are slightly soluble in water. However, this slight solubility is sufficient to make the water very contaminated. So that makes the problem really a bigger problem, because we have a source zone where you have a lot of oil sitting there, and small amount is dissolving over time, and that small amount is contaminating a large volume of water. So unless you remove the source, it's tough to keep cleaning on the groundwater without removing the source. This is just a schematic. I should have had the reference for this one. Just schematic showing how D-NAPL, we have a pool of TCE or something like that, or PCE that's going into the ground, and how much of a problem it becomes. You have the NAPL comes in above the water table. You will have some residual over there, so the vapors that are coming out, those will cause vapor intrusion. If you have houses close by, that's a big problem to deal with. Some will stay residual, and then some of it will go below the water table. If we have sand, fractured clay, we have a residual zone, and then we have a transport where the dissolved phase is small amount, but yet contaminates a large volume, and that happens over time. Volatility, these cause vapor intrusion above the water table. They have high density, it tends to stick and stay within some of the soil particles, and they have low absolute solubility, so these contaminants remain persistent over time. And low partitioning, so no retardation unless you have a high organic content of the soil, and some of them, of course, have low degradability. The contaminant partitioning becomes a factor when we talk about things like an NAPL phase. So if I take a chunk of soil over here, separate into solids, these are soil particles, and voids, and the voids I have water and then air bubbles. Contamination comes in as a NAPL phase. It will be distributed between these three phases, and it's just a schematic that shows how these will be distributed over there. So we have a NAPL phase, that's the free phase oil, and then I have a soil phase, that's the soil particles where contaminants get absorbed on it, but the absorption happens usually through the liquid phase, and then volatilization happens above the water table and generates some vapor. The reason I wanted to mention this is that to keep in mind which one is the mobile phase. This is the groundwater contamination or the vapor intrusion problems. the contaminants go into the pore fluid, and that's where it moves. While the bottom one, either it's a NAPL phase or a solid phase, it tends to be immobile or residual. NAPLs may shift, may move laterally here and there, but tends to be within the soil pores, and their dissolution over time takes a lot of contamination into groundwater. And then if you clean up the groundwater and you keep the source, the contaminant will persist, so that's why source zone removal is an important challenge and aspect of what we do. Vapor intrusion, that's when the vapor starts going above the water table into people's houses. Transformation, just for the sake of time, transformation happens in the pore fluid over here. So if I have a PCE type of contaminant, it will go transformation depending on the conditions. So this is in solution. It will go from a PCE to TCE, DCE, and then vinyl chloride. That will change the properties. This is a measure of how they will be absorbed on the soil particles. And as they do the transformation happens, their absorption and their interaction with soil and mobility will change. So maybe become more mobile. And not only that, vinyl chloride is more toxic. So just by transforming contaminants from one form to another does not necessarily mean that we cleaned up the site, because we may end up with some byproducts that are more toxic than the source. So keeping this in mind, we'll just move on and talk about the remediation aspects of things. These are important processes to keep in mind when you talk about remediation. We talked about soil and groundwater characteristics and heterogeneity, which affect the approach and the contamination, contaminant properties, and their soil-water interactions. Mobile phase is usually the one that's in solution or vapor. That's where exposure most likely to occur. If you have a groundwater well, you pump in the water from the groundwater, and that's where the dissolved phase is. But the immobile phase, that's where the source is. Just a quick slide showing that when we talk about contamination in soil, we have to just make sure that we understand that some of it is in the pore fluid, that's the moving groundwater, and you measure the concentration based on the volume of the groundwater, so it's mass per liter. There is a precipitated or adsorbed on the soil surface, and we use sorb, which is massive contaminant adsorbed per dry mass of soil, and sometimes you hear part per million or part per billion, just mass per mass type of concentration. NAPLs are mainly described by residual saturation, how much is residual NAPL you have in the pore fluid. So with this introduction, this is very important to know again about the soil contaminant interactions to understand how to approach remediation. Remediation, according to EPA, is the treatment where we permanently and significantly reduce the volume, toxicity, or mobility of hazardous substance. And you can think of removal, treatment, or containment. Removal, of course, is the best option if you can remove or destroy the contaminants. That's your goal. You can treat them to either less harmful chemicals, either by transformation process, whether it's chemical or biological. And bioremediation is an example of treating these contaminants, changing their form from a toxic to a less toxic form. Containment, if you have a source of contamination that is significant, you need to protect yourself, but you don't have an effective remedy or it's difficult, you can just go to containment so that you minimize the potential for exposure from that contamination. So we look at it from a source, a pathway to a receptor. Source, that's the source zone that I mentioned. It's usually an adsorbed type of contaminants on a certain media or a residual non-aqueous phase liquids of organics. And in the pathway, that's either a vapor intrusion or a groundwater flow that we access to it through a well water. And that's where we have the receptors. And the protection depends on what we're trying to do. We, of course, would like to remove the source or at least have control on the pathway, either by transformation or by containment. And ultimately, our goal is extraction, destruction, if not, then containment or immobilization. Source removal includes technologies that are treating the contaminants at the source. Breaking the pathway includes technologies that hinder the leakage or limit the spread of contaminants, usually, again, at either groundwater or vapor. And we can another approach is hinder the contaminant to reach the receptor by changing the land use by regulation. When we talk about remediation, we can start by, of course, our first option is if we can recycle these chemicals, that would be the best option. But usually they're in the ground, and best thing, we can either destroy them, transform them from a toxic to a non-toxic form. If not, then we would like to be able to remove them from the ground. If not, we would like to stabilize them so that they don't move around and they be contained at certain location, stabilization, immobilization. If not, then our last option will be to contain these hazardous waste, these contaminated sites. When we do an actual process, we can group them in different ways. I thought it'd be good to group them based on the processes that involve biological processes, physical or physicochemical, chemical processes, and thermal processes, or a combination of these processes. If you think about biological processes, we use either microorganisms, bacteria, or plants. If we use microorganisms, usually bioremediation. If we use plants, that's phytoremediation. And the objective of these technologies is to find ways to either break down the contaminants or extract them from the soil, if we're talking about plants, through the root phase, using the bacteria again or the plants. Most of the time you will need to either add additives if you're talking about remediation, bioremediation, to enhance the degradation and the ability to transform the contaminants. Natural attenuation is, again, natural process where you can have biodegradation happen without having to inject chemicals, but you do monitoring, making sure that the contaminant concentration decreases over time, and that could be an option. Advantages, they can treat a wide range of organics. You can use different kind of media, soil and groundwater. There is usually, if it's successful, especially talk about bioremediation, little or no residual contamination, flexibility in system design, it can be cost effective. Of course, limitation, you can only degrade certain types of organics, although theoretically you think you could degrade all organics, but some organics are very persistent and slow, and the process becomes limited also by site heterogeneity, because you want to inject chemicals or additives to enhance these processes, and you have clay, you have different media that affects the delivery of your nutrients and additives. And you may have some challenges when you talk about mixtures of contaminants, because not each bacteria or each culture deal with certain type of bacteria, certain type of contaminants, and other contaminants may not be able to degrade them at the same time, so you may have to adjust. Physical or physicochemical processes use physical characteristics of the contaminants and the site to extract or treat the contaminants. A couple of examples. One example is soil vapor extraction. Soil flushing is another example. You don't add any chemicals. You just simply try to extract the vapor, the contaminated material in groundwater or above the groundwater and treat it outside. Physicochemical processes, we can use some kind of a permeable reactive barrier where we use the hydraulics of the flow and we intercept it by a reactive barrier, and that physicochemical, because it involves the flow and transport, the flow of the contaminants as well as the reactivity within a barrier, and electrokinetic remediation where we use electricity also to move contaminants within the ground. And an example of a permeable reactive barrier, it was very popular at certain times. Basically, introduce a reactive wall over here. That reactive wall consists of certain material that can interact with the contaminant, react with the contaminants, and a common type of reactive material is a zero-valent iron filling. So you have iron particles sitting within this wall and react with the contaminants as they come in and treat them, and they come out clean. You can have it a continuous wall or some kind of a funnel and gate where you guide the groundwater contamination coming into a reactive zone, and then the water is supposed to come out clean out of the system. So this is more of a physicochemical process. Its advantages apply to different contaminants, different media, relatively low cost, but can be expensive depending if you start doing some reactive walls. Limited by site heterogeneity, may require a long time because you're just intercepting or doing vacuum extraction of the vapor phase. When you talk about permeable reactive barriers, they have also many problems, such as uncontrolled reactivity. If I have a zero-valent iron in the wall and then this contaminant comes in, if you have other things, they will react with the iron and then it corrodes and then clogs, and that can cause a lot of problem. And it did happen. I did have cases where these problems clog the barrier and then suddenly become impermeable, and then groundwater is going around it. Chemical treatments mainly try to find ways to change the contamination properties, make them less toxic by most of the time chemical additives, or these chemical additives either, in one case I mentioned solidification stabilization, that mainly to immobilize, but our preference is to do either oxidation or reduction, so we can add either sometimes oxygen-releasing compounds or hydrogen-releasing compounds, depending on what contaminant we're dealing with, and we try to generate an environment that is oxidizing or reducing, so you break down the contaminants by oxidation reduction into less toxic chemicals. Again, has advantages and disadvantages. The media limited by site in contaminants environments, requires site characterization, extensive sometimes. Cost can be significant because right now you're pumping chemicals into the ground to change the chemistry. Health and safety can be an issue, but sometimes it's a problem because you need to induce a lot of chemicals in the ground, and the reactivity, most of it may go not necessarily to treat your target contaminants. So you need to optimize the release of these chemicals, have them occur at a certain rate that's being used for specifically transformation of the contaminants. Otherwise, the cost will be significantly high. Thermal processes, you use heat or sometime to change the properties, either to immobilize. This is used in the past for vitrification. You just melt everything so that it becomes a whole together and becomes immobile. Or you can use it to generate vapor and do soil vapor extraction. In your heat, you enhance desorption and enhance volatilization of the contaminants that allows you to capture them by a process like a soil vapor extraction, which I'll just give a quick overview of that. It's not applicable, of course, to inorganics because you do volatilization. You need to have material that's volatilized. May not apply to liquid or saturated media. Talk about mostly the vapor phase above the groundwater table. So I'll talk briefly about some of these in not necessarily more detail, basically maybe repeat some of the things I've said, but go into some specifics. Soil vapor extraction, you have, let me just go over here and then come back. You have a, let's say, an L-NAPL, a light non-aqueous phase liquid like benzene plume that comes in, sits on top of the water table. Some of it dissolves and go with the groundwater, but most of it also volatilized above the water table. So what you do, a vapor extraction, you put a well over there and you apply vacuum and then take these vapor that is contaminated and treat it off in a treatment unit. This was done a lot in the 80s and 90s, especially with, and it's very well established technology. It's commonly used for when you have things like an L-NAPL type of contaminant, gasoline type of contaminant. And now even with TCE contamination above ground, that's above groundwater table, you could use something like that. So you apply a vacuum or a negative pressure to reduce airflow through the partially saturated soil, the beta zone, which is above the water table. You enhance volatilization and remove the volatile organic compounds. You may run that vapor through a radioactivated carbon to kind of absorb and remove the volatile organics before you discharge the air. And you would, the more you vacuum, the more desorption and release of volatilization will happen, and the more you will absorb by your system, and that will enhance removal. So it requires a vacuum pump, an extraction well, air-water separation to remove the condensed moisture and vapor treatment unit. It's applicable to volatile organics, those with relatively low water solubility and low partitioning potential, low ability to absorb on the soil. Just again, the schematic where you can take the vacuum and treat the vapor out of your vapor zone. Because you're vacuuming air from soil, you really need to have a media that is relatively porous, that's easy for the to have a significant airflow or vapor flow. The sand, gravel up to silty sand type of deposits will be manageable. The factors that would affect again is the porosity, water content, and heterogeneity of the area you're trying to clean up. So you need a high air permeability, relatively high air permeability within the area of remediation, and those are affected by porosity and water content and heterogeneity. Sometimes you can use an impermeable surface, a liner or geomembrane or parking lot that's above the area we're trying to apply this, so that it will help, it will enhance and improve the efficiency, because you minimize the release escaping through the surface of the vapor. You would do a pilot test to determine and validate the design parameters, and from the pilot test you see the influence, how much vacuum you need to apply, and how does the pressure change over a distance, and you develop a radius of influence based on that pilot test. So if you, hypothetically, you have a contamination area over here, so you design different wells that are spaced and the overlap, and that is the radius of influence, where when you apply the vacuum and you're taking the contaminants out of there, you make sure that you're covering your contamination area. Most of the design parameters go into the design of the distribution of these extraction wells, and also the units that needs to be used and what kind of radius of influence it will produce, or kind of optimization of the two. A simple pilot test can help you figure out the radius of influence and the units to use. So you have apply vacuum, and then you have gauge to measure the changes in the pressure over distance as you are vacuuming at a certain rate. And from the measurements, you can decide what are the factors you will need for the radius of influence, and calculate how much of the mass that you're extracting based on Q, which is the flow rate, and how much average concentration you would have of the contaminants in the vapor phase. So you design what is the extracted air flow rate, that's Q. You design the radius of influence, and your performance parameters, you measure how much mass change over time as a function of the flow rate and the average concentration of the contaminants removing from the vapor phase. An example of a pilot test result, if you look at the vacuum as a function of distance from the well, you could see it drops, and how fast it drops, it depends on the soil properties. If the soil is sand and gravel, it will go larger because you'll have a larger radius of influence. If you have a lower permeability or a higher moisture content, then that tends to be closer to the well, and then you have a lower radius of influence. And then, so you decide, this is in a log scale on the x-axis, again, the change in the vacuum as a function of distance. You can decide the radius of influence based on what is the minimum, the cutoff value that you need for vacuum as a distance from your well. So this is similar, but in this case, we have, let's say, multiple units. One unit gives me a certain flow rate, and different ones, cubic feet per minute, and then depending on what is your cutoff value, you could see you can have different radius of influence, and based on that, you design which unit to use based on and decide what radius of influence. So you optimize what unit you will have, how much flow rate it will give you, and how much vacuum it will provide you, and what will accordingly be the radius of influence, and that's what involved in the design of something like this. You can enhance the process by, these are, for example, the vacuum wells that you have. You can have some wells where you do air sparging. You pump air into the ground below the dissolved phase. So this is your LNAPL, your gasoline, This is the dissolve phase, and this is the vapor phase. You're vacuuming over here from the dissolve phase. When you add air sponging over here, it will enhance the volatility of the contaminants and allow you to accelerate and enhance the process. I still have time. So bioremediation, I have talk about that. Again, the objective of bioremediation is a process where you use the bacteria that's present in the soil to break down or degrade the contaminants, specifically the organic contaminants, from a toxic to a less toxic or non-toxic form. The biodegradation could be aerobic or anaerobic, depending on are we using oxygen or not as an electron acceptor for the bacteria. So it reduces the aqueous concentration of contaminants by biological degradation, and that leads to a reduction in mass. The contaminants can be mineralized, that's our goal, and break them down completely, or at least to non-toxic forms if we go to biotransformation. The question is that the contaminants must be bioavailable, and we also need to have the conditions that are appropriate for bacteria to be able to break down the contaminants. So you have a carbon source, electron donors, you have an electron acceptor, you have the microorganisms where there is an electron transfer happening over here, either mineralizing the organic contaminants or, again, transforming the contaminants into a less toxic form. If oxygen is the electron acceptor, it's aerobic. If not, then we're talking about anaerobic biodegradation. And which one to use for what, of course, that depends on the type of contaminants you have and what type of transformation mechanism you look at. So if you have aerobic, most of the time you're looking at oxidation of the contaminants. If you have benzene, something like that, or BTEX type of contaminants, those tend to be oxidized. Anaerobic depends on what is the source of electron. That changes what type of process you're looking at, and that changes what type of contaminants you will be treating and how much. It also depends on the redox condition that you have at the site. And that's, of course, aerobic is usually a fast process. Anaerobics tend to be slower and takes longer time. What type of biological process we have depends on the redox condition that are next to the contamination. If this is the contamination source where things dissolve and move away, as we move away, the plume or the contamination transformation changes depending on the presence of oxygen and the ability of the bacteria to use other material as a electron source. So of course, this is what learn on biological processes and how, as far away, maybe over here, oxidizing conditions, aerobic, and then as we get closer, it tends to be reducing in anaerobic, and closer to contaminants, it becomes extremely anaerobic reduction zone. And whether you want to oxidize or reduce the contaminants depends on what you're looking at. For example, BTEX, PAHs, PCBs, well, BTEX, PAHs, maybe let's talk about those. Those tend to be easily degraded by aerobic process. So if you have contamination over there, all what you try to do is to provide oxygen to the area to allow the bacteria to grow and degrade these contaminants. But it will be tough to do that by anaerobic process. But if you go to chlorinated ethenes, the PCE, TCE, it will be tough to do that by aerobic process, but maybe doable by anaerobic process, although tend to be slow. And as we go from chlorinated to less chlorinated, the ability to oxidize or reduce will change. So PCE will be difficult by aerobic process, but vinyl chloride may be doable by aerobic process with oxygen. On the other hand, PCE may be done by anaerobic process. As we go to vinyl chloride, it becomes difficult to do by anaerobic process. And remember, this is transformation. We took PCE to vinyl chloride, so you have to be careful if you're doing PCE. Are you approaching it by anaerobic process and producing vinyl chloride? What do you do then? How do you further transform vinyl chloride to a less toxic material? And sometimes you use a two-zone where anaerobic starts and then you convert to aerobic once you get to a vinyl chloride. By the way, the ones are highly biodegradable and the fours are not biodegradable in this case. Another thing is that the contaminants need to be aqueous. So you can have an NAPL phase, but that source zone will be very difficult for the bacteria to penetrate. The degradation happens in the pore fluid, where the contaminants are in the aqueous phase, and that's where you need to think about those relationships we talked about before, the salt phase, the anaqueous phase, and the gaseous phase. Take those into an aqueous phase, and that's where the bacteria can break them down and eat the contaminants. The efficiency of the process, it depends on the availability of electron acceptors or donors, depending on what you're looking at, aerobic or anaerobic. It also depends on the availability of nutrients and the appropriate bacteria to do these processes. You need to supply, if you have lack of these additives, you need to supply them. If you're doing aerobic, you need to supply oxygen by different methods. And the challenge is you need to have, for example, if we're talking about aerobic bioremediation, is you need a continuous source of oxygen, because as you inject oxygen is being consumed, you need to do more. The heterogeneity of the system can affect your ability to deliver these contaminants, so you may end up with a problem called biofouling, where you have too much growth of bacteria in one zone, and that prevents the delivery to beyond that zone. And the presence of low permeability versus high permeability soils affect that one. I have a few slides about solar power remediation, which is what we are working on as part of the Protect Center. And this is, again, a different process. So what we're trying to do over here is use redox manipulation. We want to change the redox conditions, oxidation, reduction in the groundwater, but we would like to drive those by electricity driven from a solar panel. In a way, our goal to make it a sustainable process where you don't have to inject chemicals. So instead of injecting oxygen-releasing compounds or hydrogen-releasing compounds or other things to induce oxidation reduction, we want to be able to generate those in situ. And that's what we do our research on. Just a schematic showing about how we envision these things. So we have a solar panel, we have wells over here, and then the solar panels connected into a pump and a treatment unit, and where we're circulating the water below the groundwater, and while we're circulating it, we either generate some reducing conditions or oxidizing conditions. Basically, we manipulate the redox condition in the ground to allow us to transform TCE to a non-toxic form or completely mineralize it, or something similar if it was a different contaminant. And we do a couple of processes. One of it, we try to make the environment reducing by using an iron anode. So we use the electrolysis over here to produce ferrous into the solution and making the solution reducing, and that allows us to break the contaminant through a reduction process. In another process, again, it's electrically driven, we produce reactive oxygen species, and that allow us to break down the contaminants and oxidize them. So if we are interested in reduction, we use this process. If we are interested in oxidation, we use this process. Of course, each one has its own advantages and limitations depending on what you're looking for. Just showing that we're looking at the transformation of these depending on the contaminants we're looking at. So let me skip this one. And this is, I think this was reduction. This one is oxidation, where we produce reactive oxygen species, and that oxidizes the contaminant. So again, going back over here, my goal is by electrolysis, change the chemistry so that when the plume comes in, it reacts with either my reactive oxidizing condition or reactive reducing conditions, and the contaminant comes out clean. Or in this case, we really inject and generate those reactive species into the contaminated green and circulate to clean up the site. One advantage of what we're doing also is that we can treat a mixture of contaminants. This is an experiment that we've done with chromium, 6, selenate, nitrate, and TCE, and arsenic. And in our process, we show different reduction of contaminant concentration depending on what arrangements we have and what processes we use. So the value of this process, hopefully, it will be sustainable so that we can have continuous manipulation of redox conditions for transformation of the contaminants. I have about 10-15 minutes, and I'll go over the next topic, which is some other related aspects. So we went through the contaminant properties and the site properties, to an overview of what remediation processes we have, and now some other aspects that are relevant is, okay, you want to do a cleanup at a site, how do you remove it from, say, the NPL? How do you remove it from the national priority list and say the contaminant, the site is clean? And this is what EPA does. It deletes a site if it determines that there is no further response is required to protect human health and the environment. And there are different ways that these sites, different criteria that these could be met. Responsible parties have implemented all appropriate response actions. Responsible other parties, those are the parties that are liable for the contamination, and those are the ones that EPA requires them to take charge of the responsibility of cleanup of the site. The other one is, I'm looking for the mouse, all appropriate Superfund response under circular have been implemented, and no further response is by responsible parties is appropriate. And or remedial investigation have shown that the release poses no significant threat to public health and environment. You didn't see anything over here regarding to the contaminant concentration went to below drinking water level or met that requirement. So these are decisions that EPA takes based on the remedial action and the process they do. And this is just an overview of the recommended process by EPA for restoration, where you go into a phase, the first phase, which is the remedy selection for groundwater restoration. It goes into a remedial investigation, evaluate the site, the contamination, the spreading, the threats, and the risk of the contamination. Feasibility study, what kind of processes, what kind of technologies we could use, how much remediation are we going to get from these ones. Then you go through a design process. How do you implement this at the site? Maybe run a pilot test. You do operation and monitoring, and then you evaluate technology performance, and if you need to modify depending on meeting the remedial objectives or not. And when everything is done and everything passes the requirements, that's where site remediation completed is done. Point of diminishing return, that will be a factor when you're looking at the technology, both in the design and remedy or modification. I mean, you have a source of contamination, you start doing remediation, you expect that the contamination level will drop. As it drops, then you want to decide when would you stop the remediation, the active remediation, and start doing long-term monitoring at the site. Of course, you would like to break it down so that it meets the regulatory requirements, but that's more cost and becomes difficult as the contaminant concentration decreases. It may be easier initially, but as the contaminant concentration decreases, it becomes more difficult and more costly. So you have to decide when you stop or when you change your treatment and try to predict whether you want to do long-term monitoring or it's just a longer time projection for contaminant to continue degradation or transformation, or maybe there is a pickup, the technology is not very effective, we need to have some modification in the process. And there are several factors to keep, and this is actually part of a report. I don't have the reference. I have the reference over here, so let me go back. Is new remedy warranted or not precluded by a legal issue? That's when you decide on the transition. On a case-by-case basis, active or passive long-term monitoring appropriate. You just, that will serve your needs. You need to evaluate each alternative based on several factors listed here. I want to see the mouse. Protectiveness, ability to attain remedial action objectives, implementability, could account for cost over there, risk analysis, and sustainability. And really, those are part of, they were included in a report, this 2012 NRC report discussed all these issues. Based on the report, they did analysis on 80 Superfund sites that were delisted and looked into MCL and long-term monitoring, meeting the maximum contamination level, maximum contaminant level, and which one require long-term monitoring. Long-term monitoring, you talk about cost also, and whether you have active or passive remediation. So based on these 80 sites, about 46% of them met the MCL requirement, Some of them did not require long-term monitoring. Some of them required long-term monitoring. And some of them did not even require active remediation. It's just because of the degradation happens naturally or some other ways that it did not even need long-term monitoring. 30% of the sites, 28%, required long-term monitoring. And this is a distribution of what really happened and what kind of conditions that allow the delisting of the site. So not in all cases, you're not looking at the MCL as the main primary goal objective of the remediation. There are other factors that come in play. Of course, we need continuous research and assessment, and this is for us this is a very expensive and very challenging problem to deal with contamination. I really give an overview to give you about what is being done and from an applied side as well as the factors that are involved. But contamination is very complex in the subsurface. You have very complex contaminants, very complex soil contaminant interactions, very heterogeneous and unknown media. And I didn't even get into finding where the contamination is and the source. And this is another big problem to deal with. I mean, you may find a plume, but you don't know where that plume is coming from, or you may think where it's coming from, and that's another challenge when you talk about remediation. So there is still a need to find ways to improve our approach and improve a way to remediate these contaminated sites, as well as management of these contaminated sites and groundwater. There are significant implications, of course, if we don't do remediation or we don't try to find better and effective ways to manage and to clean up and manage these contaminated sites. And those we have to keep in mind and keep promoting the need to really clean up our water resources and reclaim our contaminated soil and environment. That ends my presentation. I'm about 1 hour almost, and I did, I think, too many slides. But I would go there maybe quickly, but I hope you find this helpful and useful and maybe answer questions.
Thank you, Akram. I don't see any questions offline right now, but I'll ask the people in attendance if you want to either chat to protect P42 or if you want to use the raise hand button if you'd rather ask your question directly. Please go ahead and do so. The raise hand button would be to the right of your name in the participant box. Are there any questions in the room itself where you are, Akram?
How about Salah's question?
I'll have a question. I wanted to just ask, you alluded to it with the fact that you're starting to use solar power for your remediation method. Are people looking at sort of the lead rating or the energy efficiency rating of remediation methods now as part of the evaluation, or do we just sort of give up and say it's really about remediation, don't worry about energy costs and other things that may be involved?
I think a lot of this has been done, and some of it is done in California. I think Mike Gill was on the audience, and they've done a lot into the sustainability and the impact. But most of the work that has been done is making sure that the technologies minimizing the carbon footprint and minimizing the impact, again, of the processes, meaning the trucking and all these things. But again, ultimately still the main goal is the actual remediation, keeping in mind the broader impacts of the active remediation. I think maybe Mike is on, he can comment on some of the things, if he's on. If he's,
Kristen, do you know if Mike is on and you can unmute him if he is?
But overall, I think just to answer the question, it's specifically to the, I mean, the remediation is still the major ultimate goal of these technologies or the approach. The question.
Is there any other concern when you have the cell in the soil of the electric field on the soil other than radiation?
So the question is that is there any impact of the when we put the electrodes on the soil other than the remediation and changing the chemistry, right? And that's a good question because you have to think about the adverse effect of the process when we're thinking about what we're doing. And I mean, the voltage and the current that we use, the electricity is very small. So actual physical impacts will be limited. However, by changing the redox chemistry, you can change the environment that is over there, and that can have effects on, for example, what type of microorganisms and the mobility of even other chemicals that are present. So these are the type of things that are very important to look at, keep in mind. Yes,
Akram, first of all, thanks. I thought it was a very good presentation because those of us who aren't scientists could actually understand it as well. But I wanted to ask, you talked about sort of the plumes and sort of the large contaminations, but what about contaminations that are slower? I think of, you know, people putting chemicals on their lawns, and sort of slowly over time is going to have an impact, I assume, on our water table, as opposed to some big, you know, immediate kind of contamination.
They do. And I think that's a good question, and maybe if I go back and look into the source of contamination that we have described over here, some of it goes, not only that, I mean, the de-icing, you know, I think some of these things, the slow release, it's not only the agriculture, it's not only the dumping of the waste over here in the landfill and all that, but all these, you know, these are things, and a lot of work is also done. Most of it tends to be local. The way the approach is either the state approach, especially you think about the use of de-icing chemicals and things like that. And I think our state spends, you know, look into that a lot because we add many chemicals that tend to contaminate. Most of the time tends to be close to the surface, but still over time it continues to go down. Actually, the DOE contaminated DOE sites, what happens is that when they, you know, in the past when the waste was dumped, was supposed to be groundwater table is very deep, and we look into areas where no shallow groundwater, and these waste will not penetrate and will not reach the groundwater, and there isn't much rain. The rain that's coming in is relatively small amount, but yet over time, that these contaminants continue to penetrate and reach to groundwater resources hundreds of feet away. So just because it's a slow infiltration process doesn't mean it's not a problem. And actually, when that happens, it makes the problem more difficult to deal with because the longer it is, the more difficult problem it is. Yeah.
Kristen, do you have any other questions from other sites?
Let me just double check again. No, I still have no other questions.
I think with that, I'll thank Akram very much for a great wrap-up to the Protect Academy series, and I want to thank all the other speakers, Ingrid Padilla, Rita Lacruso, and John Meeker. And a reminder that all of these talks are archived on the Protect website, and I believe that Kristen will be sending out a SurveyMonkey poll after this talk for you to provide feedback, and that'll help us in the future as we go forward with the Protect Academy. Kristen, do you have any other announcements?
No, that's it. Thank you all for attending.
Thanks, everyone.
All right, thank you. Have a good day.
Bye-bye.